Hello and welcome to another LeetCode video. Today we're going to be working on find peak element, and this is a similar problem to the one I did before, which is find peak element in a mountain array. However, in this problem there's a difference. In this problem, your array can have multiple peaks. So let's go through these examples. So for this 1, 2, 3, 1, and we can return any of these peaks. So in this 1, 2, 3, 1, the peak is 3, and then in this one here, 1, 2, 1, 3, 5, 6, 4. There are multiple peaks. There's a 2 peak and there is a 6 peak, and we can return either one of those. And so we need to return the index. And there is a little bit more to this problem. So in this problem, they say that if your anything outside the array is less than anything in the array. So for example, if you have something like this, get rid of this. Okay, so if we have something like this, laggy, okay, 2, 1, and then this can be whatever, this is a peak because anything outside of the array is negative infinity. So that's a peak. And then also, if you had a 2, 1 here, that is a peak as well because anything outside is negative infinity, anything out here is negative infinity. So that's a peak and that's a peak. So that's all other things you need to know. And so let's actually go through the second example and figure out kind of how we need to be doing this. And we are asked to calculate it in a log-in time. So we are going to do a binary search, but let's just go through what we need to do for this example here. Okay, so we're going to have 1, 2, 1, 3, 5, 6, 4. So the first thing we're going to actually do is we're going to check if the out of bounds, like if these two are peaks, which is pretty straightforward, right? We're going to check if these two are peaks. And if they're not, then we can just say, okay, well, then we're not going to include those in our binary search because we're going to be checking to the left and to the right of the element. So because we're doing that, we actually want to start our left and right to be the second element and the second to last element. So our left is actually going to start here, and our right is going to start here. And we're going to preemptively check these before because we're going to be comparing elements to elements in front of them and behind them. And so we don't want to have like an out of bounds error, right? Like if we check here and we check for an element in front of it, there's nothing there. So we don't want to do that. You could also start here and here, and you could also just have like an if statement there where you could just say like, if this is 0 index, then let's just say we're out of bounds. But I'm going to do that outside of the code. You could do it either way is fine. So we're going to start here. Now, what are we looking for? So this is going to be pretty straightforward. Let's actually kind of draw what this looks like to give us a better idea, right? So we're going to have 1, 2, 1, which is going to look like something like this. So 1, 2, 1, and it's going to go up to 3, and then it's going to go up to 5. So let's just do like this. Then it's going to go up some more, 6, and back to 4. So let's actually draw those, right? So 1, 2, 1, 3, 3, 5, 6, 4. I need to make this a little bit bigger. There we go. Okay, so that's what we have here, and these are our points. So let's figure out what are we going to be doing. So where's our first pivot value going to be? So our first pivot value is actually going to be, and let's actually draw this in another color just to make it a little bit clearer. Our first pivot value is going to be in between the left and the right, right? So it's going to be right here. So our first pivot value is going to be here. And we're going to ask ourselves, like, we're going to, you can do this in a few ways, but we're going to compare our element to the element after it. So we're going to compare the pivot value to this element here. We're going to say, is the pivot value greater or smaller? And in this, they didn't write this, but in this problem, every value is either greater or smaller than the one after it. So you're never going to have like 4, 4, 4, 4, 4 or something. Okay. And so because of that, let's ask ourselves, we're going to compare to our next value, and we're going to say, okay, is this 3 greater or smaller than the 5? Well, it's smaller. So if it's smaller, then we know there is at least one peak that's to the right of this pivot value, all right? We're guaranteed that because we're smaller. So since we're smaller, we're going to say, okay, well, we can just get rid of this whole part of the array because we know there's at least one peak over here. So then we are going to make our left over here. And now this is our new searching region. And we got rid of this whole part of the array. So where's our next pivot value? So our next pivot value is actually going to be over here. Okay. Well, now, so this pivot value is gone. We're over here, and we're doing the same thing. And actually, this whole part of the array, this whole part of the mountain is basically crossed out now because we got rid of that. Because we know there was a peak somewhere over here. So we're going to do the same thing. We're going to compare to the next element. We're going to say, are we greater or smaller? Well, we're smaller again. So if we're smaller, we know that there has to be a peak that is somewhere over here, right? There has to be a peak. Because there's two conditions, right? If you think about it, either it keeps going up and never comes down, which means the last part is a peak, or it comes up and then comes down and then there's some peak here, right? So if the array ends at like 5, 6, then we know that 6 is a peak. But we know from our previous work that the last element is not a peak, so our case is always going to be this. But either way, it would work. Okay, so we know that there has to be a peak here. There has to be a peak here. So where are we going to move? We're going to move to the right again, right? So we're going to take this left, we're going to delete it, and we're going to move to the right again. So let's actually change the color there again. So our left is now going to be over here, and we're deleting this whole section of the array, and we're deleting this peak as well, essentially. So now our left and our right are in the same value, so obviously our pivot has to be the 6. And so let's draw that out as well. So our pivot is going to be over here. And now we have to check again. Okay, are we greater or smaller? Where we are greater. So if we're greater, that means there's two things that are possible. Either we are on the downslope, right? Like a pivot's here, and we're checking over here, and we are greater, but there's still something greater here, or we are the peak. And so we're going to check the element to the left, and we're going to say if we're greater, then we're the peak, and let's just return. And we are greater, so let's return. But if we were not greater, if we were on the downslope, then we know that our peak has to be to the left of this peak. And then we would just move our right that way. Okay, so let's actually write down all these steps just to get a better understanding. So 1, check for endpoints, or ends of array, to be a peak. If yes, we just return right then. Okay, otherwise, let's make L and R the second and second to last elements in the array. Okay, and now for our checks, let's get a pivot. If pivot is less than pivot plus 1, that means that the peak is to the right of the pivot. Otherwise, if pivot, so let's just write that down before. If pivot is greater than pivot plus 1, we have two cases. We are either on the downslope or we are on the peak. So then we check for the peak by comparing to pivot minus 1. If it is greater, if pivot is greater than pivot minus 1, then we have the peak, right? Then return the peak. Otherwise, so if we're on the downslope, right? Once again, if we're on the downslope here, if we're on some downslope peak, then we have to go left. So otherwise, the peak is to the left. And we're guaranteed to have at least one with these cases, right? So let's go over it one more time. So we check the ends, we make the LNR the second to last elements, we get a pivot. If the pivot is less than the pivot plus 1, that means we're on the upslope, so we're like here somewhere, and there's a peak that's to the right. So we just need to get rid of all this stuff to the left and go to the right. Otherwise, if the pivot is greater than pivot plus 1, so this would be like pivot plus 1, that means we're either going down or we are at the peak. We check the element to the left. If we're greater than both, then we have a peak. Otherwise, we need to just go left in our binary search to go to the left side. So now we have everything to code it up. It's pretty straightforward once you recognize, like, we don't really care how many peaks there are. We're just looking for one. And so there is guaranteed to be at least one peak in the direction we're going if we know if we're going up or down. If we're going up, there's a peak that has to be to the right. And if we're going down, there's a peak that has to be to the left. Otherwise, we are the peak itself. Okay, so now let's actually code that up. So the first thing we're going to check is if if our ends of the array are a peak, right? So if length nums, so if you actually look at the constraints, length nums can actually be 1 in this case. So if length nums equals 1, we only have one element, and that has to be a peak. Or nums 0 is greater than nums 1, or nums -1 is greater than nums -2, we can just return here. Actually, we want to do these separately because this will give us two different values. So if either one of these is the case, that means the first element is the peak, so we can just return 0. And then we need one more check here. So this is the case for that. It's the case for that. Now let's do our second check for the, so let's be if nums -1 is greater than nums -2, that means our last element is the peak, so we can just return length of nums -1. Okay, so now that we removed the first and last element, now we can just start with the second to last element. Now we have these comparisons that we can freely do without worrying about going out of bounds. So I think it's more easy. It's like an easier way to do this problem as opposed to doing left equals less than, or left is less than right. We can do left is less than or equal to right, but I'll show you here. So we're going to say left equals 1, and then right equals length of nums -2, right? Second to last element. We could say while left is less than or equal to right, we're going to get a pivot. So we can just call that p even, just make it even easier. P left plus right over 2. Now what are our conditions? So if nums p is greater than nums p plus 1, or I guess let's do less than first. So nums p is less than nums p plus 1. Yeah. Then that means we are on like the upslope of the mountain, so we need to be going right. So we can just say in that case, let's just say if we need to be going right, we need to do left equals pivot plus 1. Else, so otherwise we are on the downslope of the mountain. That means p is greater than p plus 1. So we need to check if we are the actual peak itself. So if nums p is greater than nums p minus 1, that means we are the peak, so we can just return here, return p. Otherwise, we are on the downslope, and then our peak is to the left. So we're going to need to say right equals p minus 1. And so we should, theoretically, in this binary search, we should always get an answer, assuming there's always a mount. And I tested this before, there is always a peak. So we don't have to, but if you wanted to, you could write like return -1 or something. Okay, I think we have everything here. Let's just double check. Local variable, right? Okay, so this is left, right. Hopefully we don't have an infinite loop. Although we might. Looks like we do. Okay, so let's just double check this. Yeah, so it's an infinite loop for something small. Okay, so let's just double check this. So if length of nums is 1, or if nums 0 is less than nums 1, that means we know that we have a peak at nums 0, so that part's fine. If nums 1 is greater than nums 2, we would return that. That's also fine. This is fine. This is fine. So if nums p is less than nums p plus 1, that means left has to be p plus 1. That's correct. Otherwise, nums p has to be greater than nums p plus 1. So if nums p is greater than p, that part is fine. Yeah, so let's think about what we did wrong, actually. Oh, yeah, right. So we have a right. So we're assigning right, but we're not assigning r. So we just have a wrong variable name. Okay, nice. So you can see it's pretty efficient. And for the time and space complexity, let's think about that. So obviously we did write an algorithm that runs in log n time, so that's pretty straightforward. So that's going to be log n because it's just a simple binary search. This is O of 1, this is O of 1, and a binary search. Okay, and for the space, as typical of a binary search, most binary searches, it's O of 1 because we just have a left and a right parameter. We don't have anything extra saved. So that's going to be it for this problem. Hopefully you liked it. Like I said, it's a common interview problem, as you can see. So I definitely encourage you to know it, and I definitely encourage you to know the difference between this and the problem where you have just one peak and like what are the different things you're looking for. They're pretty similar, but yeah. So if you did like this problem, please like the video and please subscribe to the channel. It helps grow it a lot. And I will see you in the next one. Thanks for watching.